Everyone, welcome to Thursday of the American Control Conference. We're here for our morning plenary, but first I would just like to make a few announcements. So just welcome you all on behalf of the OPCOM. You can see Santosh, Cam are here on the webinar this morning. We all welcome you this morning and thank you for your support of this conference. Really appreciate the help of all the session chairs, everyone creating their videos, uploading their final papers and registering for the conference. It's really wonderful to have everyone's support and make this conference happen. We really appreciate that. Also just want to point out some of the new innovations at this year's ACC. So originally we were not planning to have a virtual online conference, but here we are. But we have some new features this year, like the rapid interactive sessions that we've been able to translate, I think, effectively into the Zoom format. We also have the Slack channel this year to help with communication. We have virtual booths for sponsors. We have special sessions. I just wanted to point out today we have office hours from the National Science Foundation. So we do every day. And today we have a special session on broadening participation at 1:30 today and a student advising session today at 4 o'clock. I do hope you are enjoying the rapid interactive sessions. So from 9:30 to 11, we have short 3-minute presentations followed by the interactive discussion at 11 o'clock. And we have, you can vote for your favorite late breaking presentation. We also have poster session during the coffee breaks. So at 9 o'clock and then again in the afternoon break. So please do go visit the posters. They each have their own Zoom room. They're in the program. And probably you've also already checked out the online program, but you can access it through the main webpage and allows you to click on the various sessions and then to access the Zoom icons that are on the right-hand side of the program. And everything is in here, not just the papers, but also the special sessions, the exhibitors, everything can be accessed through this online program. Also want to point out that the program will be available until August 15th. So you can watch the videos, download the papers, but after that, it will no longer be available, and then you can access the papers through the proceedings like you do for previous years. We'll also have a PDF of the conference program, but it won't have the PDFs and videos available after August 15th. So we have a strong technical program, and we encourage you to nominate favorite paper for the Hugo Schuck Best Paper Award at the ACC, and also in the rapid interactive sessions to nominate Best Paper in Session. We already have those results for the Wednesday, but they'll all be announced on Friday afternoon. We have a great set of plenary talks, and this morning we're very pleased to introduce Professor Andrew Aline. I'll turn it over to Santosh now.
Good morning, everyone. I am Martha Grover, Program Chair for the 2020 American Control Conference. Please ask questions during the talk using the Q&A feature at the bottom of your screen, and Professor Aline can answer them during the talk as well as after the talk. I am so pleased to introduce our plenary speaker this morning. Professor Andrew Aline holds the Ralph M. and Catherine V. Fisher Professorship in the College of Engineering at the University of Illinois, Urbana-Champaign. He's also the director for the NSF Engineering Research Center on Power Optimization for Electrothermal Systems. Professor Aline joined the faculty in UIUC in 1994 after completing his BS at Princeton and MS and PhD at UC Berkeley. Professor Aline's research focuses on the modeling, simulation, and control of nonlinear mechanical systems with a current focus on transient thermal systems. His academic record includes supervision of over 80 MS and PhD students in over 400 conference and journal publications. He is the recipient of an NSF Career Award and is a fellow of IEEE and ASME. Last year, the American Automatic Control Council awarded him the Control Engineering Practice Award. He was also awarded the UIUC College of Engineering Teaching Excellence Award, the UIUC Campus Award for Excellence in Undergraduate Education, and the UIUC Campus Award for Excellence in Graduate Student Mentoring. His extensive professional service includes chairing the ASME Dynamic Systems and Controls Division, and he is a member of the IEEE Control System Society Board of Governors. His record of campus service includes the Associate Dean for Research in the College of Engineering and the Associate Head for Undergraduate Programs in Mechanical Science and Engineering. On a personal note, I very much appreciate Andrew's mentorship and support. I was an undergraduate student in ME at UIUC during his first years as a faculty member, and Andrew has been an unflagging source of support and guidance through my first years as a faculty member and to this date. Andrew, thank you for accepting our invitation, and we look forward to hearing from you about your latest work.
Hello, and thanks for the introduction. My name is Andrew Lean. I'm from the University of Illinois at Urbana-Champaign, and I'd like to thank the organizers for having me here to talk to you today. And I'd also like to thank all of the audience out there, wherever you are in the world and whatever time zone you're on. We'd like to talk to you today about the control of complex energy and power systems for electrified mobility. Now, the outline of the talk, as seen here, is going to start off with a little bit of a motivation, and I think for folks who are not familiar with this, it's important to know why this is an important problem. Then we're going to do some modeling. Everything that we do in our group is model-based for the most part, and then we're going to take those models and do controller design on them. I want to spend some time doing a specific design example using some of the control design techniques that we developed in the previous part of the talk. And this is going to be on a hybrid electric UAV, and I'll show you sort of why we're looking at a hybrid electric UAV when we get there. And then finally, I want to wrap up really quickly on some stuff we've been looking at for the last year and a half or so on integrating design with control. So you're designing the plant and the controller at the same time, and then finish up with some conclusions. And if there's time left, take any questions. Before we start, I do want to go ahead and give a shout out to the students, past and present, who are the ones that have really done the work that you see here. These are outstanding students. I'm up here presenting, but they're the ones that really sort of did all of the work. Now, the motivation that I want to do, sort of diving into that, is electrification here is a mega trend for all mobility sectors. I'm showing aviation here, and we'll have a lot of aviation type of examples, but it's not just aviation. It's on highway, off highway, marine, you name it. If you're moving around goods and people, you actually start to run into challenges in efficiency from a purely mechanical or electro-hydraulic or a mechanical hydraulic system. The electrification is one that really starts to afford a lot of benefits in terms of efficiency and capability of the systems. And you look over time here, okay, as you went from just first putting onboard electric generators on aircraft all the way to more electric aircraft that use electrification instead of bleed air to move air around your system for your air conditioning or what have you. And people are even talking now about electrified propulsion of the actual vehicle. There's been a corresponding increase in the capacity of electric power, and this is actually a log scale here. So if you look out here, where we are sort of in 2020, the more electric aircraft, the Boeing 77, current versions of the 7087, they have about 1.4 megawatts of power running through that system. As soon as you actually start talking about increasing power, the key thing that you have to worry about is power density, or power to weight, kilowatts per kilogram is very important in the aerospace. In the terrestrial on-highway applications like cars, it may be kilowatts per liter, for example. But that's still a density metric, okay? To tackle this idea of power density, we started a center, a National Science Foundation Engineering Research Center, on the power optimization of electrothermal systems. Just a brief synopsis, our whole goal, our target, is to increase power density using a systems approach. There are folks that have actually tried to look at increasing the efficiency of the electrical system, improving the thermal management systems, but we're one of the few center level types activities that really take this systems approach that allows you to balance off the electrical, the mechanical, the material science aspects of different subsystems. There's 4 universities, Illinois is the lead, I'm the director. Arkansas, Stanford, and Howard are also participants. This is sort of the ecosystem, and all of these companies or agencies are ones that we've interacted with, discussed with. They're either part of the center or have been approached and are considering being part of the center, or we work with in adjacent associated projects. And so we have government, OEMs, first and second tier suppliers, and small businesses. POETS itself, it's a 10-year ERC. We just went through a renewal. Runs 2015 to 2025, and it's about a $40 million grant from NSF. Now, currently to date, in addition to the first $20 million, we've already brought in over 15 million in additional external contracts with the partners to date. So this is an area that is of significant interest to our partners and basically to the world as a whole. And I'll give you just two examples, one from industry and one from government here on the aviation side. I could do easily other ones from the automotive side or the off-highway side, but let me go ahead and load this up. This is an example that is from Raytheon Technologies, which is an industrial partner for POETS. And what they're trying to do is they're trying to take this Dash 8, add some batteries and a motor, and actually electrify one side of this twin engine aircraft, replace an engine with a hybrid electric system and batteries. And as you'll see in the video here, there are good reasons for doing that, including increased efficiency.
Most regional airliner flights last 1 hour, time roughly divided equally between takeoff and climb, cruise, and descent. Today's regional aircraft use a 2 megawatt class engine. At takeoff, the engine runs at full power, then levels off to 1 megawatt during cruise and descent. The Project 804 engine also delivers 2 megawatts of power in a 50-50 split between a 1 megawatt engine and a 1 megawatt electric motor, working as a parallel hybrid electric propulsion system. At takeoff, both the engine and motor run at peak power, together delivering 2 megawatts of power. Leveling to cruise, the electric motor throttles back while the engine continues at 1 megawatt optimal performance for the full flight. Traditional engines are fully optimized but have limitations that are well understood. Changing the game with hybrid architectures opens an entirely new optimization space. And opportunities we are studying for in-flight energy recovery can mean even more efficient performance.
So that is the government take on this. Sorry, that's the industry take on it. And not just the industry is interested in this, the government is interested in this too. ARPA-E, I want to talk a little bit about the ARPA-E program, the Ascend program. Basically, this is a $35 million program that is just about to kick off, and it's only for the motors and the drives, the power electronics. Santosh, is Santosh still there? We seem to have lost sound. Is about 2 kilowatts per kilogram. Based on some of the projections that DOE has done, if you can get up to about 12 kilowatts per kilogram, you're starting to become competitive in terms of that decarbonized aviation. As you'll see, trying to get to this level, integrating what goes on in the electronics and in the thermal system, controls is a real critical enabler, because sometimes the electrical system may overtax your thermal management system, and your thermal management system may have to go back and tell your electrical system, shed some of that load, throttle down, I can't handle all of it, if you want to go ahead and make it through the end of this mission. And that's one of the key things we'll be showing in some of the results, how these things integrate. So hopefully you believe me that the government and industry are putting significant resources into this electrification of mobility. And I could do something similar with automotive. Many of you sort of have seen automotive vehicles that are electrified out there, and I'm sure there are many other sessions at the conference this year that talk about this. I want to move a little bit now to the modeling aspect of things. Okay, now what are some of the requirements? For these types of systems, they span multiple physical domains. They span thermal domains, mechanical domains, electrical domains, and this is a figure taken from basically an MRIP document from Eric Walters and some of the folks at PCKA working with AFRL. And you could even throw in here chemical conversion if you think the engine is a chemical energy that it has to convert from the fuel. But the takeaway point is that I can mix and match different engines with different electrical systems. So the models have to be modular. Moreover, they should be scalable, so I don't have to use a completely different framework for doing UAVs versus doing that Dash 8 that I showed you from Raytheon Technologies. The model should be easily reconfigurable. When I want to sort of figure out many different types of designs and run through a design space, I should be able to go ahead and reconfigure these models without investing a huge amount of energy and effort to make it happen. Obviously, the models must be accurate if you're going to do model-based control. And one of the things we run across a little bit more recently, is they should support design optimization for these types of complex systems, because that's where the real benefit is. Aircraft in particular, they can go 20 years between generations, and so you have to try a lot of what ifs before you commit to actually the design that you're going to actually be building. And so this is really useful for early stage design. The approach that we take to make these things modular is to represent the system as an oriented graph with nodes and interconnections. And representing these systems as a graph really helps when it comes to controller development, as we'll see in a bit. The graph form, also what's really nice, this is an enabler for the design optimization tools we'll talk about at the last part of this talk. Basically, they look like conservation laws, okay? And so the vertices here, they're energy storage vertices. And the rate at which you store energy is basically equal to the net power in minus the net power out. And so the rate of change of energy, and here this is just a capacitance type term, and the amount of energy that's stored in here is equal to the sum of the powers in minus the sum of the powers out. This is a linear equation. However, the power flow between two vertices along this edge here, and note the arrows is just, it's oriented, it just makes equal for sign convention. This is not a directed graph. These terms here can be linear or nonlinear. As a matter of fact, they're mostly nonlinear. This is where our nonlinears lie in these edge connections. You can go ahead and assemble all of these models, and there's a slew of papers we have on this, including V&V, where that full graph model, I can rewrite it in this compact, almost state space type form, where I have a capacitance matrix, an incident matrix, and a matrix which dictates how my exogenous signals, my sources and my sinks, flow into the overall graph from almost like boundary conditions, if you want to think about it that way. Now, these types of systems, as I was saying, you'd like them to be modular and scalable, so they can be used for many different types of systems. It's scalable, as I'll show, from components to systems. Here's a power electronics, it's an inverter. You can kind of see the inverter, the little red square here is the active the chipset. This greenish looking, it's a gap pad, a thermal interface material that takes the active elements out to these finned heat sinks once you actually fold this part down on top. I can actually cut this up into voxels and come up with a graph that's purely thermal. This is a purely thermal graph. And out of that, in this paper actually that came out last year in IFAC CEP, we did some nice model reduction to make things run a little bit faster. But you can see we're actually doing a pretty good job of predicting temperatures. Similarly, for this hybrid UAV powertrain that we're going to talk about a lot in the design example, right? I can actually have an electrothermal graph where the green and yellow ones are electrical and the red vertices are thermal. You don't have to know the details of this. You can just see it has kind of sort of a tree type structure. If I try and look at things like the battery voltages or the currents or mechanical variables like the prop shaft speed, you can see you actually do a pretty good job of capturing these. So the same type of, and this was presented last year at the ACC, the same type of approach, this graph-based modeling approach of power and energy components, of power and energy movement can be scaled from individual components. Like this inverter here would be something that would be sitting, let's say like inside that orange box, all the way out to a full system. And this system here, this is basically the guts of a UAV, but splayed out on a couple of test benches in a lab so that you can actually do the testing without actually flying it. They're scalable. They do V and V. They do it pretty well. Okay. Now, once we have these graphs, the thing that we really like to do is move from the graphs to a hierarchy. So if I take a look at a notional aircraft architecture here, I've got, this is like half an aircraft. Right? It's cut down the middle. I've got an engine. Usually you have two engines, unless it's a fighter or tactical aircraft. I have a engine, and I can basically bleed off of that engine high pressure air to run an air cycle machine. This can be like air that cools things. I can have electrical systems. Electrical systems run through some bus into some loads. And we have two different types of loads that we put on the bus. We have things that are called flight critical loads, which means you have to go ahead and service those loads. Otherwise, the plane falls out of the sky. We have mission critical loads, where if you don't service those, you don't complete your mission, but you still get to go home. Okay. And then you can have other elements, fuel tanks off the generator. This is a heat exchanger to pick up a lot of heat off of maybe an oil cooler that's trying to cool the generators. Generators get real hot. And you can see, this is actually just a notional architecture. You can see this type of reasonable complexity. It's not huge. What we can do is rearrange all the elements and identify them by timescale. So each of the energy storage elements here, I can enumerate. Okay, and then I can basically cluster them by the type of power that flows, whether it's thermal power, whether it's chemical power, like from the fuel tank to an engine, whether it's mechanical power to the shaft. Now, what I can also do is figure out, which one of these is slowest and which one of these is fast. Obviously, the electrical systems are going to be really, really fast, right? What is the slowest thing here is the fuel tanks. It takes a while for the fuel tanks to lose all their mass. Fortunately, I mean, you'd like the fuel to stay in the aircraft. And also they're large enough that if they change temperature, right, it doesn't affect things too much. It'll change temperature relatively slowly. Note, one of the things that's actually important for aircraft is that you have to keep the fuel temperature below a certain level. A lot of times the fuel is actually a heat sink for these electrified aircraft. You will actually route the heat through some cooling loop and dump it into the fuel, except that you can't, once the fuel gets to some upper level constraint, and you can kind of see where we're going here with some type of constraint optimization that will run online, you can't accept any more heat into the fuel, and so you go ahead and cut it off there and tell the electrical system, you have to go ahead and back off if you want to do any more until I can recover my cooling. I can agglomerate these by time scale and break it down into the overall vehicle system. And what's contained in here is an agglomeration of individual nodes, where some of the dynamic nodes in the previous graph end up being algebraic, and you reduce the model of the system. Similarly, you have a thermal system, which is a reduced model of the system. And these are broken down. Now you'll have your thermal subsystem 1, thermal subsystem 2, and the electrical system, you can have multiple electrical subsystems as well too. And this electrical subsystem here, this is the thing that's providing a disturbance to the thermal subsystem, what the thermal subsystem is trying to reject. Okay, this thermal subsystem is also feeding information up to the vehicle to tell the electrical system, here's the max amount of power you can draw right now, based on what I think I can accomplish now and a little bit in the future. This hierarchy is one that we're going to use over and over and over again. That particular hierarchy, based on the example that I showed, is one based on timescale separations. And it was for an aircraft example. Similar techniques can be used for other types of electrified vehicles, and we have. There was a paper that Donald Dawsimo postdoc did on a hybrid electric on-highway vehicle. Same type of example we actually also did for a journal mechanical design paper that just came out this year. And what's nice about the graph-based approach is there are actually multiple ways for system decomposition. We just did it by time scale, which is kind of sort of like looking at eigenvalues. You can also do a min cut based on power flow, max power flow through each of the edges, spectral methods, an agglomerative clustering method. The one that Donald did in the CCTA paper was basically based on an input-output distance sensitivity metric that he formulated to show how to go ahead and cut this up into different levels of system level hierarchy, vehicle level, system level, subsystem level, and then individual components. You can sort of think about those as individual pumps or switching on the electrical system. So now you have the system in a hierarchy. Okay, what do you do with it? Right? And here's where we get into the controller design. Well, what we advocate and there's a long reason why. I'm happy to talk with people offline about it. It's something that we've evolved over many, many years, is this hierarchical control architecture. That allows us, particularly for the multi-timescale example that I showed before, it allows us to do control over multiple timescales. Now, the hierarchical approach, I set up a hierarchical model, or system representation. If I do hierarchical control, we advocate that this is agnostic to whatever algorithm you use. You can use whatever algorithm you want at each of the individual levels of the hierarchy. You choose the most appropriate algorithm. We found that MPC is very good for the higher level ones, and you can see an MPC algorithm here doing sort of vehicle speed tracking, an animation of that. At the lower levels, running an MPC is not feasible because they're so fast. What's happening at the lower levels, and so usually use simple types of PI or the type of rule-based algorithms that run pretty fast. The reason why this hierarchical approach is good, particularly for online optimization approaches like the MPC, is that the MPC, it is computational constrained, right? And distributing the MPC in that hierarchy, up and down that hierarchy, affords a lot of computational tractability. Let's say the maximum number of steps that you could actually compute is 10 steps, k equals 10, with the compute resources that you have. What you can do, if you have a centralized MPC and you run it at the slowest time scale, right, you could look pretty far into the future with those 10 steps, but you might miss disturbances that come in between each of your updates. Okay, so it wouldn't resolve decisions sufficiently fast to meet the disturbance requirements. Simultaneously, a centralized MPC could run on a very, very fast time scale. It would catch all of the individual potential fast disturbances that might come in, but you wouldn't be able to look very far into the future. So breaking down the problem into subproblems allows the lower level controllers that are most likely to see fast stuff coming in to react very, very quickly, whereas the upper level controllers, which sort of govern what's going on and things don't change as quickly at the upper level, they can actually take bigger steps and look further out in time. And that's one of the big advantages. One of the questions you have as soon as you have this hierarchical approach is, how do you make sure that the system stays stable? How do you know the system is going to stay stable? Well, here we take advantage of the way that we represented the system. So we represented the system by these graph-based models that are based on energy conservation. Right? These models can be shown to be passive, and Justin Kellum, who's now at UT Dallas, did some nice work showing this in a couple of Automatica papers a few years ago. So you can show that these are passive by the conservation of energy law. Now, what happens is when you interconnect these systems, you can show that the power flow and the interactions between subsystems or among subsystems, if there are multiple ones, but just between two of them, they follow this negative feedback formulation. It can be recast such that there's a negative feedback. If I have negative feedback of two passive systems, that's overall going to be passive. So I can show that the interconnected graph, and that's what Justin did here, he showed that this interconnected graph overall system, it's passive. Okay, the open loop, it's passive. What happens when you put the controller on here now? Certainly you can drive the system unstable if you put a poor controller on there. What his idea was, and it was a very good idea, is to go ahead and introduce a controller, right? So you augment this interconnected passive systems with a controller that's passive, and you enforce controller passivity as a constraint. So you put a negative feedback loop on your controller here with this subsystem here, I, for controller I, right? And you make sure that controller I is passive, and I've got a passive interconnection of a passive system, it's going to stay stable. Now, the additional thing that he did, which was kind of neat, is that he relaxed that. So this controller here doesn't have to be passive always. Because it's running this MPC at the upper levels, right, what it can do is it can actually enforce passivity as a constraint. Right? And so it's almost like integral passivity. So over the entire window that it's looking at the system, right, formulating the control sequence, it has to be passive over that entire window. It can be it can be non-passive over some fraction of it, just as long as over the remaining part of that window, it's sufficiently passive to extract energy out of the system that would swamp out what you had in that previous piece that was non-passive. And making the passivity a part of the MPC constraint is what really affords a lot of flexibility in this approach. And if you put this type of controller near the lowest part of the hierarchy, you can be sure that you are going to stay stable with respect to the actual plant, independent of what the upper level controllers are doing. And beta here is a tuning value to say basically how much passivity you want to build up. So that was a very good idea, and that sort of led to a building block for something else I want to talk about, which was these systems. One of the things we found, particularly for aircraft, but it also happens for cars as well too, sometimes they have in their cooling loops or in the electrical loops, they'll have switches that switch on and off. I will switch out a cooling loop and turn it off because it's cold enough, I don't have to cool it anymore. And rather than just waste power, I just go ahead and shut off the pump or shut down a valve. Same thing for an electrical system. If I don't have a light load, why am I running both generators? I just shut one generator off and just run from the other generator off of one of the engines, rather than run two of them apart load and run very, very inefficiently. And so you can actually have these things turning on and off, and what happens is it changes the topology of the graph. Okay, so how do you go ahead and make sure that under this changing topology of the graph, the system overall stays stable? Well, Herschel Pangborn back in 2018 basically came up with a way to do it. Oh, and by the way, even if your topology doesn't change, for a lot of these systems, we actually do a linearization when we do our controller design for the MPC, so we do a linear MPC. And if I'm doing multiple successive linearizations and I'm changing the models, that's kind of sort of a switching approach as well too. We don't do like continuous gain schedule, we just do finite switches to keep the model size, the number of models small. We use a similar approach, basically. So instead of individual subsystems now, these are individual switched subsystems. They still have this negative feedback interconnection, okay, to retain passivity. So if the switch system here is passive, and I go ahead and put it in connection with this other passive system, then you can show that this overall system is going to be passive, as long as the graph stays connected for all the switch model representations. The connectivity is important, and that's one of the things that he showed. And you can generally prove that this interconnection of switch subsystems is also going to be passive. And similarly, just like before, you go ahead and have this controller now, which enforces this integral passivity constraint. And it's going to be feasible. Basically, you can show that there's always going to be an input that satisfies some function of the output which makes my integral term here less than or equal to 0, or enforces passivity as this constraint. Now, normally I've got my controller that's acting and trying to sort of stay passive enough with the switch system. We all know that switch systems, even if the individual ones are stable, if I switch amongst them, there's no guarantee it's going to stay stable. What Herschel did was, use the commonly Lyapunov function approach to show that the switching really did give you overall stability of the system. The final controller approach that I want to talk about here is robustness. Right? You can do a robust to two things: model uncertainty or to disturbances. We're going to talk about the disturbances here. This is another way we exploit these graph-based systems. So the classes of graph models here, not to beat a dead horse, is they're based on energy conservation. And these models here can be shown to be state affine, okay? Which means they're linear in the states, which is in contrast to the previous work on passivity, which was input affine, not state affine. What we can show is that if these systems are what they call cooperative systems, right? I'll get to that in a second. You can create robust positive invariant sets from extremal equilibria. So basically, you can take worst case situations in terms of things that would come to your system, and from that figure out very efficiently what RPI sets are. And the benefit that you use these things called cooperative systems, where you have your state dynamics. These are the state dynamics we had before. Here is the state evolution, if you will, as a function of initial condition, time, and exogenous signals. The system is going to be cooperative if my exogenous signal bounds another one. A PB is upper bounds PA, and this can be element-wise in time. And I start off my trajectory XA, upper bounded by XB, then over time, the state trajectory related to B is always going to overbound the state trajectory related to A. And that's a type of system that's called cooperative. And it's related to monotone systems. And on the previous one, you saw some nice references where we borrowed heavily from that monotone systems literature. And the upshot is we use this for robust control. I can have the switched system. Here's my system running along, and I can have my switched inputs or my switched states, a plant model. And so I can think about having a linear system here that looks like it's a switch system where sigma is the switching signal. And this is what sort of Herschel did to wrap up for his PhD. And if I break the system up into a hierarchy, right, level 1 can choose a mode at each step and pair this with an equilibrium-based RPI set. Right? And it's very efficient to compute because basically we don't have to work with general polyhedral sets like with tube-based MPC. We can basically just compute maximal minimal trajectories by plugging in maximum disturbances into the dynamics, and this makes it much faster to solve. And it makes handling this subsystem at level 2 much easier. And so you have these robust positive invariant sets that are very easy to compute as I move forward in time. And this says at the upper level, I start off here, I just have to stay inside this invariant set, and then my next invariant set just has to start off where this first one left off. What's nice and what he showed is level 2 here, running at the faster time step, it reduces the conservatism of the upper level because it allows you to go outside the robust positive invariant set. You can go outside it as long as you get back in before the next update from the upper level controller. And so that gives a fair bit of reduction in the conservatism. And what you did is you did this in a simulation and a experimental system. Show the experimental system next, where I have a heat load that gets applied to a particular heat exchanger, we call it cold plate, in this thermal management system. As you can see, there's 4 different subsystems in here, a bunch of different heat exchangers, valves, pumps, what have you. But big picture takeaway, I'm applying this pulse load, and you can think about this. The gray is how much heat that I want to reject based on the electrical load that would come in, right? What we're showing is the cooling system when we design it, okay? This is just showing that, mass flow rates in certain pumps, pump 4, are going to go on, off, just showing you what I was talking about in terms of having a switch system that will actually change. What you actually, you can't meet the load because you start getting close to your max temp. And so the gray that's up here, that's not covered by the red, is the load that's shed, and you have to tell the electrical system, no, you have to make do with what I can actually provide you underneath this red outline. And the important thing about what Herschel was just talking about in terms of the monotone systems and cooperative systems that allows you to relax things, you can actually see that this blue line here is the robust positive invariant set that will be set up by level 1. But clearly, at each excursion, if you look at the blow up here, the level 2 allows the trajectory to go outside of these bounds, okay, as long as they get back inside of these bounds before the next update. And effectively, you can kind of sort of see this actually happened when they did an experiment. This is an IR system, and in simulations, you could actually see that we're getting this excursion outside and coming back in, or excursion outside and coming back in, allowing basically more heat to go in. So the electrical system got a little bit more electrical energy it could use to run its units. And the experimental system looks very similar to the simulations. Okay, I'm speeding up here because I'm running a little short on time. Now, what we showed here, this looks great, but there were some challenges. We did a wonderful hardware-in-the-loop study, just came out earlier this year in TCST, in Transactions Control System Technology. And you can see Malia here running this hardware-in-the-loop system. This was a thermal setup, and back here is a DSpace system that's running a simulated aircraft and the electrical systems in there. We did a significant performance improvement over a baseline approach. That was all detailed in TCST. The baseline approach had, I think, 35 to 40 different PI loops running, plus a bunch of different logic. It was a sizable activity. The performance, you can see, it does very well in terms of key performance parameters. The blue is the baseline, and basically smaller is good. So if you lie inside the blue on any one of these axes, that means you're doing better. You use the same amount of energy, but basically you do much better at minimizing problems with the temperatures, which was a little bit of the focus of this system. Now, in doing this, we assume full state feedback, okay? Now, the thermal side alone for this particular hardware-in-the-loop experiment that was in this TCST paper had about 40 states. And for practical implementation, we need an observer to estimate the states. We couldn't do full state feedback with 40 states, and then all the electrical states on top of it. And there's similar challenges to control. We have multiple dissimilar timescales. So we had two options, a centralized observer or a hierarchical observer. And you can probably guess by now that we went with the hierarchical observer. And the hierarchical observer estimator for the hierarchical control, so each subsystem observer estimates its corresponding part of the system, and it receives coupling information from observers above. So you take this observer here. This observer, which is above it, gives it coupling information, meaning what this part of the state is going to do. Whole overall state space gets passed down here, as well as any information that's coming from the vehicle level. That gets passed down in terms of coupling terms. And it receives measurements from the lower level. If the lower level is also an observer, it receives the estimates, or we call pseudo measurements. If you actually happen to be at the lowest level, the measurements that are coming up are actually the measurements you're taking off the actual vehicle itself. At the vehicle level, it estimates the entire vehicle using a reduced order model and receives these pseudo measurements or estimated values from the level just below it. This gives much lower computation requirement. You'll see in a second. Not quite an order of magnitude for the test that we did, but significant. It's modular, so I can swap plant systems in and out and don't have to redo the estimator. And it does accommodate these multiple timescales, like we said. For the example that I'll show, we use common filter formulations at each level, just to make it easier. And the estimator convergence, there's some nice work that just came out in JDSMC, and she submitted. Pamela submitted some work to CDC, and we'll see if that gets through, where you can actually put bounds on the estimation errors as a function of time, where basically it's upper bounded by some class K function, an exogenous signal bound, which could be like noise, and those coupling effects that I talked about, the coupling effects to systems that propagate up through the observer directly above you, that then propagate down to you. And you can see when we actually did simulations and experiments, the bound function was valid. Blue is the bound, and orange is the actual error, the estimation error, and the bounds do hold. When we wrap this all together, show you a couple examples. You can kind of sort of see, this is just for a thermal side of an overall vehicle. That hierarchical estimation really provides a good trade-off between estimation accuracy and computation complexity. It's not perfect. You'd get better estimation if you actually did a centralized system. And you can see at the lowest level, the estimation's pretty good. It starts to get a little more granular as it go up the second level. At the top level, you can see there's a fair bit of a little bit of a delay, and it's kind of granular. But for these types of systems that we're working with, this is actually sufficient to do pretty good controller design. And you can kind of sort of see, this is a controller example using observed results. And I'm showing you another example here. When you sort of hit your cold plate temperature limit, basically you throttle down on the amount of load that you allow that electrical system to use, and you go back and tell the electrical system to shed this, if you will. That's not. I mean, the controller works with the estimator. But what I really want to show is what happens if I try and use a centralized estimator to do a very similar type of control design, where these are different cooling heat exchangers, and they're being hit with different loads. You can see this one here, it's got that very pulsatile type load. This one has pulsatile, but on a much longer duty cycle. This one said it got random. If I do a centralized approach, it's got over 5 times the computational load versus the distributed hierarchical observer. And in this case, sometimes at these points here, it actually just fails to compute. The cycle time comes up again to do an action before you've finished computing your observer and your controller. And so these are the count sort of like controller failures. Yes, the centralized observer is going to be a lower error if I look at the error overall, but it's no guarantee it's actually going to solve it in the time scale that you want. Whereas the hierarchical controller, it does very well at the lowest level, but as I go up in level, yes, I lose accuracy. It just depends on whether or not this particular threshold of estimation error is detrimental to your overall controller performance. And in a lot of systems, it's not. Now, I want to go ahead and talk specifically about a particular design example before we wrap up, and we'll see if we have enough time to do this. So what we have here is there's a company called Area I. We worked with it a little bit. They built a product that's called an air-launched tube integrated unmanned system, the Altius. The idea with this Altius, this particular one here is a hybrid electric UAS system, and it's tube launched. So air launch, tube integrated, means that you could be flying, and then you've got a tube here, almost sort of like a rocket, where you'll launch the system, will fly out and look ahead, and there's a sensor package in here that it can actually survey and see what's going on. And if you're able to play here, you'll sort of hear the music going. It's got a little funky beat. Right around 30 seconds, you'll kind of see a key element where they're able to turn the engine on to recharge the battery in flight. And that's the key element of this air launch system. Right now, so you're able to go ahead and turn the engine on, turn the engine off, charge up the battery pack, run on battery for just a little bit, and then go ahead and turn the engine on when you want. It's a very neat type of a system to package all of that together and put it in a system that you can actually go ahead and launch by air. It doesn't have any landing gear because the landing, these are supposed to sort of go out and take a look, and when they land, it's sort of like a controlled crash. The landing gear don't really fit well when you sort of roll it up and fit it into a tube. And that is the motivation for this type of a system that we have here, which is my guts of that type of Area I Altius system splayed out on a test bench. This is the experimental platform. We do our graph-based model with the converter, the heat exchanger, the battery pack, the fluid tank, the vehicle body. And we can actually, we have some tools where, given the V&V'd components, we can actually mix and match them using some composability algorithms to actually come up with sort of an automated composability of different systems, which is really nice if I want to go ahead and do my design optimization and try different system representations. Now, for this particular system, it is an electromechanical thermal control design. And as a design example, I'm going to have MPC that will do sort of vehicle speed tracking. I've got an overall mission planner that plans out my battery state of charge so I don't run out of battery when I'm in the middle of a place where I really want to run on battery and I don't want to have to turn on my engine. I plan thermal types of cold plate temperatures and heat distributions to make sure so my electronics may not get that hot. This overall system, it's got about, again, 70 states, 16 inputs. And so what I'd like to do is start with a simpler problem and just look at the electromechanical piece. I'm just going to look at the electromechanical piece here. Okay. And In doing so, I've got this upper level that does battery state of charge and load planning. I've got a vehicle speed reference and a genset coordination, whether I turn things on or off. And then at the lowest level, I just have PI regulators to regulate maybe current on my genset, for example. And I have various controller evaluators. I can look at performance, so how well I'm tracking my reference, let's say my speed reference, or how well am I tracking my loads for my electrical system. A reliability objective, am I violating constraints, in particular the temperature constraints, or in this case, we're going to see the battery charging constraints. If you throw too much current into the battery too quickly, that can be detrimental to the battery over time, and fuel efficiency. This is the simulation of a mission profile. And so you take off, cruise at lower speed, go up to pretty high speed, come down and cruise at low speed. Maybe you loiter, you're looking at something. And while you're looking at something, here's your base avionic load. And once you start looking at something, that base avionic load gets really high. And then it drops off as you sort of trying to get out of where you're looking and accelerate. A couple of things happen here. The mission planner up here, a baseline approach that we use is kind of sort of like a charge sustaining approach. The mission planner sees somewhere here in the mission that you're probably going to run out of juice because to power the engine and the battery. In the dash segment, you want to actually use them both. And so it recharges right prior to when you do the dash segment, so you're able to come back down and get through that dash segment very, very quickly. Another thing that's interesting is that, so that's a proactive recharge. That's basically this state of charge. You can almost think about the upper level controller coming up with a virtual barrier function or constraint set of state of charge that you want to make sure that you don't go below in that hierarchical approach. As you go ahead and drop from your high load avionic load to your low load avionic load, right? The baseline controller, all of a sudden, when this load goes off, you're generating a lot of current to service that load. That load goes off, you spike and throw a lot of current into the battery. Negative battery current means you're charging the battery. And if the battery has a limit, let's say of 10 amps that you can push in there and you double that, that's actually not good for the battery life. Whereas a hierarchical approach is able to look out ahead with its predictions, and actually it doesn't go ahead and violate that constraint. It just rides right up to the battery max current constraint by being proactive in turning down the genset, the amount of power that comes out of the genset. And on a bunch of different figures of merit, here smaller is better. You can see on fuel consumption, so we actually run an engine in the lab. There's about a 10% reduction in fuel consumption, and in terms of the violation of the current constraints and meeting the speed tracking of my vehicle, it does very well. If I throw up the experimental results, it almost looks like exactly the same thing. And so this is another demonstration of why we're pretty confident that these graph models and the V&V that comes out of it are good. It doesn't change very much. Given time, I'm actually going to skip over when I combine everything back together in this hierarchical electrothermal coupling approach, and we can come back to that in the Q&A section if we have time. I want to spend the last 5 minutes talking about something here where we integrate the design with the controller. Okay. Now, going back to motivation, the motivation part's important. There is a whole new generation of eVTOL aircraft being proposed. And this is just one motivator. There could be many, many others. Right? Here, Uber Elevate is one example of trying to do these eVTOL systems. There's 8 companies that are part of this Uber Elevate network, and each company is developing its own eVTOL concept. That's an electrified vehicle that can do vertical takeoff and landing. The question you might ask is which one is best, or how would you go ahead and design it when you have like a clean sheet design and you've got to go through, I mean, it's almost pretty much like the Wild West of vehicle design. You don't know what is the right design. You want to try out a bunch of different ones, right? How do you optimize the design for the system while also optimizing the control strategy? Right? And here is where our graph-based models really come to assist us again, right? If I want to change the system and its functionality, it's equivalent to changing the graph that represents the system. So if I want to change the size of a component, right, that's basically the same thing as changing a vertex or an edge. Right here, I could actually go ahead and change, vertices, okay? Increase this one, increase the power flow through one of these edges, and that is changing the design of the physical system itself. I can actually change the topology of my system as well too by removal or addition of an edge. So I can have a system that's connected like this, right? And if I remove these edges, that's a new system, and basically this vertex 2 would be taken out of the design, and I'd only be left with these vertices 1 and 3 here. So the way we can do this is, remember I had the design, I had the graph model that said sort of C, negative MP, D, P in. Well, I can pre-multiply each of these with these design matrices, psi and phi, where psi is sizing design variables and phi, or phi, is topology design variables. The topology design variables basically go for edge addition or removal. It'd be like zeros or ones. The sizing design variables, it would be basically a scaling factor that you'd use to either increase or decrease the size of your node. If you want to do the edge sizing, that could also be on side, but now it's not 0 or 1. Now it's a scaling factor, and this allows for really easy relationships between design variables and graph-based models that we use. And Donald really led a very nice Journal of Mechanical Design paper that sort of outlined how to do this. Let me show you how it works. And here we're going to look at an electrothermal hybrid energy storage system, or HESS example. So hybrid energy storage systems combine power-dense ultracapacitors, and you can put a lot of power, but you can't store a lot of energy, with energy-dense batteries, where you can store a lot of energy, but you can't go ahead and get the power in and out that fast without damaging them. And a hybrid system combines both, where the battery takes the low-frequency stuff, and the ultracaps take the high-frequency stuff to meet a load that has sort of high-frequency and low-frequency components. We're going to focus just on the electrical aspect here, and shout out to Scott Moore out at Berkeley, where we got this from one of his papers. Carrie Laird, who's one of the students, did the electrical and the thermal in ASME DSCC, and also in this ACC, I believe. But we're just going to focus on the electrical part here for the sake of time. So I can represent this hybrid this hybrid energy storage system using the same state space type model that we had before. And here is basically a layout of how it would look in graph form. We use a simple PI control architecture on both the battery and the ultracap to limit the currents and get good bus voltage tracking. Bus voltage tracking right here and right here is where I'm getting very high current changes due to pulsatile loads that might come onto the system. We put the pulsatile loads on the system intentionally because it'll give the PI trouble to track. And I know we could use different types of controllers, but this is just for the sake of illustration of how you can do this co-design. So the figures of merit you want to look at right now, just to make it easy, just focus on the deviation from the nominal of the bus voltage. What we can do is we can augment our state equations with these design variables, these design matrices here. And these design matrices quantify the impact of changing the design variable. And for simplicity, we're just going to go ahead and use diagonals, or we'll just change the values in this diagonal matrix, in the diagonal in these matrices using our optimization tools. The sizing variables specify the HESS design. Theta here are maybe the number of batteries and the number of ultracapacitors. The gain scaling variables specify the controller. So alpha and beta are basically scaling variables that I put in front of a nominal P control and a nominal I control gain. Okay. We can set up a multi-objective optimization function, which corresponds to whether I care more about the size or whether I care more about the performance. And here, performance, we're going to go ahead and let's focus just on the bus deviation, the voltage deviation on the bus. We can also put in constraints on our controller parameters as well as our plant parameters, and then you use your favorite numerical tool. Here we use GAs. This is a very non-convex problem, as it turns out, and so if you try and use gradient methods, you got to be pretty careful. But the takeaway is that if I optimize the controller, and so you can see the blue here is the optimized version, the Ki and the Kp gains changed for my battery control and for my ultracap controller, right? For the initial design, the optimized approach has a significant reduction in the voltage ripple. You can see that here. The blue is much, much smaller than the red. But at the same time, it's about 50% smaller than the initial controller. So I've shrunk this system. I've gotten it smaller, which is good for power density, and I've also got it to perform better. And in that shrinking, I've actually reconfigured what percentage of batteries I use and what percentage of the ultracap I use based on the duty cycle that I'm actually running. And this is sort of laid out also in that DSCC paper. And in that paper, Kerry also shows that, you know, look, you could design the optimized plant and then put a very good controller and tune that controller for that optimized plant. But actually, if you design the controller and the plant at the same time, you can do better than if you do either one separately. For sake of time, we'll skip that. So wrap up here in conclusions. The controller development for complex systems like these electrified mobility, it really does start with a modular and scalable approach to representation. These graph-based models are an effective representation for the power flow through these different systems. Power could be mechanical power, electrical power, thermal power. Graphs can cluster in different ways. We showed a lot on timescale clustering, but the bottom line is to get it into this hierarchical form, because those hierarchical models integrate well with hierarchical control and multi-level hierarchical control, not just supervisory control where there's an upper level and then everything else. Right? And hopefully I convince you that these hierarchical control strategies are really the best way to go about meeting tight constraints, trading off between different subsystems, and forcing something to shed something if something else is more important. It's that coordination amongst disparate subsystems while achieving the system goal that I'm talking about. It's far superior to simple local or decentralized loops. And in that hierarchical control, we did a lot of MPC, but if you want to use other types of approaches, you can use those as well too. I'm a big fan of doing architecture and then doing the algorithms. And so, you know, I'll leave you with the right framework here of the architecture with this graph-based approach. Really enables both these hierarchical control algorithms, but also these integrated design and control algorithms that I showed you sort of in that last little bit of a snippet. So with that, I'd like to acknowledge the students that I've had over the years that have worked on these problems for electrified mobility, as well as the sponsors, both within our Engineering Research Center, as well as ones that we work with outside. And I will go ahead, wrap up, and take any questions. Thank you very much for your time.
Thank you so much, Andrew. You worked so
cutie.
hard. We worked you so hard during the talk. So glad to see all these questions. Maybe you thought you would have it a little bit easier because it was recorded. But thank you so much.
I did. I was busy the whole time.
I saw that.
How would you like me to handle questions? Shall I go ahead and read them? I know folks have to get off and go to other meetings. Or
Yeah, how about reading one or two, and then, but then we want people to be able to get to the posters. We have posters for 9930 and exhibitors. So how about picking one or two to do live, and then you can stay on and do them through the Q&A, or, you know, until 9:15. We have, but I do want people to get to the posters and exhibitors.
Agreed.
Maybe just pick one.
I will, go ahead.
After the couple of questions, Cam, you can give the host over to Andrew, and that way he can continue till 9:15 if he wants.
Say again?
After the couple of questions, we'll close the session, but you can give the host over to Andrew. So
he can still stay on. Yeah, he's a panelist, so he should be good. Yeah.
I'll start off with the as they came in. Huai Li asked, what about the change of topology and design optimization for if you have large-scale changes to your system? For example, for a hybrid electric vehicle, there are series and parallel configurations, and there is a great deal of complexity. And would you be able to go ahead and, in a nutshell, handle more complex systems to do the controller and the plant design at the same time? The answer is yes. The Journal of Mechanical Design paper that we showed was for a hybrid electric vehicle, and we were considering not necessarily series versus parallel, but some of the topology changes on air versus liquid cooling. But we can also do series versus parallel and consider a lot of different things. It just depends on the optimization approaches, because it's a very non-convex problem. And so the optimization problem scales up pretty quickly and it becomes very computationally intense to try and find solutions as you start to search the space. So the method extends. I will say that we have run into computational challenges, and so a big part of what we're doing right now is trying to see how we solve these large scale non-convex problems more efficiently. We're just at the start of them. I mean, you asked this question here. Interestingly enough, the partner that we're working with this is an automotive company on that exact problem. It is in the solution space for the optimization. The framework holds, right? I say I do architecture first, then algorithm. The architecture, the framework about how we try and solve these problems, the putting it in this framework has given us a solution path that we hadn't had before. It's finding the right machinery to do it effectively, or just a bigger hammer, a lot of computing power. And with that, I want to be respectful of people's time. So if folks got to take off, do I just stay on this channel now, Cam, and everybody goes?
Yeah,
I think people should go on to the next session, but but you can stay, but people should also move on.
And I'm off in the next. I got about 5 minutes on this one. So
that's good. We'll all have to leave by 9:15, otherwise I won't be able to start the ROP session.
So I think maybe let's close the session, and because Andrew can always answer questions by email, and there's a Slack channel available, so it's all good. So thanks everybody, and thanks for the excellent talk, Andrew. It was fantastic.
Yeah, thanks again, Andrew. That was a great talk.
Thank you. Thanks for the interest. Thanks for inviting me, Martha, and thanks for the kind words.
Okay. Bye, everybody.
Bye. Thank everybody. We'll see you soon. Bye-bye.
Session's going on now, so
yeah.
thanks.